Welcome everyone for High Performance Computing, Advanced Scientific Computing. Today we have our lecture 3 on Parallelization Fundamentals. And if you remember at the beginning of the course, I said we base lots of experience on student feedback, and hence we had always a little bit the assignments later in the course and so on, because the practical aspects, for instance, what we learned about MPI was coming a bit later in the course. Usually we had more, let's say, theory to base on, right? Like the parallelization fundamentals today. Hence, a bit lecture 2.1 was a bit out of sync in the general understanding of HPC, but that is not a big problem because now you can at least work already on the assignment 1 very early in the course so that not everything comes at the end. And secondly, we had learned indirectly already a little bit of this parallelization fundamentals when we talked about broadcast, for instance, that one certain processor or one process, more accurately, is taking the role broadcasting to everyone, and with this also taking a special role. Or if you remembered our ping pong program, right, these were also interesting elements. So let's connect nicely what we had the last time in our practical lecture 2.1 of what we want to do today. And this is something where you already should look a little bit again on the boundaries here. So when we say we have the idea of one process sends something to the other. So obviously here's this memory boundary we discussed, right? We cannot access a memory just like that as a processor here. We have to use send and receive. This is what we had already used actually in ping pong. Now I don't go into the details of it, but think about it that in this respect, we already sort of divided our application logic in two parts, where we said, okay, this is something, a role taking ping and the other role take pong. Very simple, admittedly. And we were extending that a little bit with the more advanced examples where we said one process here, it takes the role of the broadcaster, right? And brings this information to others. So another idea that you have here, maybe what we would sometimes say a little domain of 4, kind of elements for an applications. You want to have 4 processes working in it in parallel at the same time. And you want to decompose that domain in a way that it makes sense. And here we had then this broadcaster said, okay, there are this kind of 4 processes. They should all work together in this. And one takes a special role of broadcasting some data to the others. So with this little experiments, you have basically learned already some of the core building blocks to do that. Of course, we want to do this in a bigger scale, and we don't want to just shift data around, although you will notice today when we come to lecture 3, shifting data around is an important concept. We will learn about halo regions, ghost layers in MPI, which are basically very application oriented. So to really cut down a domain, we will understand what a domain decomposition is, why basically also load balancing is a very important aspect to talk about. But let us review further what we had with the important idea of the communicators. They also will come back to us in the Cartesian communicator in the next lecture, which then already alludes to something, again, very visible and very intuitive to a domain decomposition we will discuss, right? And we learned that this MPI COM world is very important for us. It has a kind of world of all the processors, and everybody gets a unique rank. That's the one information I get from this beautiful MPI environment. I start from MPI init until MPI finalize, right? So we get this important information out of the MPI environment. What role do I play in the big role of all the processes? So which rank I have? And then the second one, how many are there all in all? And we learned that this information could be incredibly useful. You have seen it in ping pong. We have seen it already also in the initialization of one of the buffers we have sent, so that only one process was really initializing, so that we could test if something was really going, so to speak, via the broadcast to all the other processors. And this is a bit the essence also what we will extend today, especially if you think about the idea what we said, a real application we want to do maybe would be the kind of element you see here. There's a river, there's a boat, and we could imagine that from the physics perspective to really calculate an application doing this realistically, we need to take into account the physics of the water flow. Hence, this could be maybe just a group 2 of all the processes working on it in parallel. So compute the physics iteratively, time step by time step, and then the interaction of the boat with the water then this would be the next, basically in the terms of physics, how big is a sail, how big is a power in one certain direction, velocity, and so forth, might be another group. And with this, you have already sort of a domain decomposition. You really have this application domain of this boat on a river, and you decompose it to parallel parts. And this is something which nicely now connects us to to our parallelization fundamentals here today. So there was one thing we already covered, and which is also important for you to realize, it was the scheduling concept of the wall time. So usually you would have an indicator of how long a job would take in order to get executed properly, to get you some outcome, because you want to run an application in engineering or basically in science to have an outcome, right? So hence you would have a certain understanding over submitting it a couple of times, what would be your kind of processing time needed roughly. And if you give that the scheduler, what you have to do usually in production, that means you can be mostly scheduled more effectively, because also we learned something like backfilling. When, for instance, one hole in the schedule exists that would fit your job, you could be even coming earlier than people that long submitted before, but had maybe much more resource requirements and cannot be scheduled right now because there's simply not resources enough at hand. Right, by doing the assignment 1, what you're tasked to do basically now in parallel, make sure to create your private and public key pair at once. As I said, that would be the most important part of assignment 1 in the beginning, because otherwise you cannot proceed with the others. You don't get an account on Elia. But let us connect now to the parallelization fundamentals. As I said, it was a bit out of sync. Normally would have this a bit earlier so that you understand already parallelization, but that's not a problem. In parallel, you can work now on the practical topics of MPI, while we come back to MPI then based on the foundation of the parallelization fundamentals with some more domain decomposition aspects like the Cartesian communicator I was alluding to. So today we will start again simple for people that really still not got the message of what parallelization entails, right? We have learned about multi-core, many-core, the different elements. So what we do with this, how we do a computing application example. Then there are certain parallelization methods. As I said earlier, domain decomposition is here a big word. We will learn what that means in this particular part of the lecture, but then of course have on and on examples throughout the other lectures. There's one important method called the halo and ghost layers, specifically also in MPI, when you cannot access the memory and you want to have time-based or time step-based applications, which is very relevant in simulation sciences. So based on, let's say, physical applications using numerical laws, numerical libraries based on physical laws. And it's equally valid for data scientists. And we have some different programs that illustrate this. Then the second part will give you a little bit more on the terms, basically the theory behind parallelization. That's now a topic where many people start already from the students here. Oh my God, now we go into lots of formulas and let's say have a very theoretical course again. We keep the theory here to a reasonable degree of understanding. So don't worry, it's still a very practical oriented course that we want so that you can really program in parallel. But there's some things in HPC you need to understand, and let's go far beyond Moore's law. Moore's law is very known in computer science in generally, so we will have just a very brief look at this. More important are elements in HPC. So what we want to do, what is a speed up? What means load imbalance? These terms are very important. Of course, then also thinking about how I can maybe have smaller formulas in order to understand a little bit more on, serial versus parallel elements of an applications, where are limits in the applications. We will learn this basically with the limits of applications. We can show them basically with weak scaling, strong scaling plots with application examples, but also have a couple of laws which are basically with Gustafson's and Amdahl's law, a very important part again of HPC terms. So let's see where we go with this in order to understand topics of the course. The key really today is the domain decomposition. You should get an information basically what is this entails on a very low level. We really start with very simple applications up to really the interactions of particles, which is already an advanced topic. But this is really more than the idea of parallel programming and why it is so complex. We just don't do one simple program and do everything in parallel and execute it on 10 cores. There's an application logic behind in a domain we want to cover. Let's say the heat in the room we discussed once, right? So this is a domain, the room. So how we decompose that to basically do the physics in parallel, meaning the heat, ventilation, air flow, combined with the windows I was explaining on the other side of the room. So this would have some interactions, plus, of course, students sitting here, me standing there. So in one respect, you will learn with this some abstractions of parallel computing on various levels, really. And this is what we will today do. And with this, you really should be able to program and use HPC programming much more advanced than you could do with MPI, because now the counterpart with the theoretical lecture, admittedly today, will bring you more an understanding on the strategies for parallelization, which are very important. So let us review quickly what we said before. And there's one element which I want to learn you by heart in a way with this slide coming this and again. Think about parallel computing is not just to have the Formula 1 here supported with the top 500, the best supercomputers and so on. The idea is to solve any computational problem we have in physics, in data sciences, in a cooperative way. And the cooperative way is now an important part, right? And this cooperative way is not something where an application is born for. So an application runs and needs to be, let's say, decomposed to do it in a cooperative way, especially if you think that we have more and more processes available running essentially in all of these different processes. Hence, this is an important part. The applications we do need parallel processing because we want to do some application logic in a cooperative way. And the building blocks we learned already for this, which is sort of an abstraction on a different level. We said here we have the multi-core CPU. Obviously, this multi-core CPUs, the core 1, 2, 3, do things already in parallel, right? There's not one idle and the other don't do anything, except you maybe have a large memory job. That's what we sometimes have in HPC. Then you maybe don't use all the cores. You're rather interested on how much memory you actually have on the chip. It's memory-bound applications. But in the end, this is on the very lowest level if you want, right? Now we thought about, okay, with MPI, we bridge this to another, let's say, chip to another memory space to be more accurate, and then you can do much more. Hence, the domain decomposition is still bound, of course, to these elements, how much CPUs, how much processors we have, how much multi-core we have. Now, let's make a simple illustration here, because I think that carries lots of good essence. Here's a domain, as we would call it, now introducing this name more and more, which is very simple, the domain of an array of 16. And then we just want to have the maximum of it, right? So this is an example, okay, admittedly very trivial. You say, okay, I want to do this with 4 cores, and each core get 4 equal chunks of this array, should report the maximum in the local. And then basically when I'm at the end of this, the max global should be the maximum of all these different 4 chunks, or as I would call it, I decompose the domain, right? This is a very simple example here. I decompose this. Nobody said that it's the right way to do it, right? I was the application guy here. I say, okay, I want to do it this way. I could also chunk it smaller, use maybe 8 cores instead, or I just use 2 cores divided by 2 in the domain. These are questions which not always are very apparent. So the application examples, the application should really allude you to this. But there's also one takeaway message that you see here. You think always that parallel computing is very, simple, straightforward, because you put everything just in equal chunks and then we're done with it. But as I was alluding in, I think even the prologue was, think about this one, right? This is also computing, might be also computational expensive, maybe at least as those maximum local ones, but who is doing this? And there's often silence in the course, because we have here one role which is basically not really possible in parallel, because we collected already everything from the local. So there needs to be one rank, already the wording for it, taking the role of taking the max global from all of it. Hence, this would introduce something we call, in an extreme situation, load imbalance, right? Because we have not just another core lying around that can do this and waiting for all the others, then this other core would have nothing to do first. Hence, one of these core 1, maybe, for instance, would take the role of rank 0, then also computing this. But while the core is doing this, all the others would have nothing anymore to do because they already had their duty at delivering the local maximum. And this becomes more apparent if you go through different larger application examples where you always have to see that the CPU should be as best as possible loaded, used all the time, right? Sort of 99%. But the realistic part of it, that's very hard to achieve if you have real applications. Now coming to the other side, and in lecture 6, we will talk much more about it. We have this many core GPUs. And I think that's important for us. I will not play the whole video. You have the reference here of the YouTube NVIDIA Volta architecture. And to be honest, there is an update on this. It's just a nice video to explain you that the cores are going more intensively to support AI applications. So not only physics application we talk in the course. But here you have also degree of data parallelism and task parallelism, which is a bit different from the multi-core CPU as we discussed already before. So GPU has just many, many tasks, right? So there's thousands of them. And basically with NVIDIA, we have already a Hopper architecture. There are new GPUs, but they follow the same idea. Although we have to say that these cores that they are inside, these many cores, they're much more special. And this tensor cores that we just saw is one example of really specifically support also deep learning, right? So this is something also to understand that we have sometimes also the architectures moving towards the application needs. So we have a simple illustration again of a domain decomposition then in this many core space we just discussed. Here you have to think about parallel computing of a matrix times, array or something like this, because you would say, for instance, in deep learning, that's what you learn in deep learning, right? There are lots of weights in a big neural network that you have to train to learn, so to speak. And this is often done with matrix multiplications or matrix vector multiplications of sorts. And when you give this to an NVIDIA GPU, but there are also others nowadays, AMD GPUs and so on, there's a nice parallelization in the sense that all of these different many cores could really solve this problem in a cooperative way, but independently from another, right? You see that quite nicely with the color coding here. The mathematical rule to compute the matrix times vector here is illustrated in the colors, having no impact on all the other parts in the color. And this independent parallel computing is another element of it, and which is important for the GPUs and also for deep learning to thrive, so that you can really scale up with a deep learning network when you have bigger and bolder GPUs. Obviously, the device memory plays a role and things like that, but we also see later in the course. But here, again, take away the message. We have a different complete problem here. Not anymore the maximum of an array or something we had before. Here we talk about matrix vector multiplication. And the beautiful thing is we have this domain that we see here. We call the domain of the matrix and the vector, and we decompose it in a way that we have the mathematical rule supported by one, part of the GPU, the other, matrix part, another part of the GPU, and that's why it works so nice. Another example of a domain decomposition, admittedly very simple, but to the point, because now when you think bigger, bolder, the whole world, right? Complex climate simulations, or what we have daily when you look into your weather app, numerical weather prediction, right? So these are very computational expensive calculations, mostly based on numerical, methods that in turn are then, of course, based on physics, law of physics, but also not only the processes in the model, also of lots of data exchanges around it. Hence, you have here an interesting sort of domain decomposition around the world. You see here basically different grid structures where you decompose the Earth into smaller chunks in order to make it computationally feasible. Then every chunk has to do its own parts of the physics, depending on the, of course, topography and all other elements that you see here, and then have, of course, to take into account what happens next door, right? You hardly can do the weather just on one spot. It depends what the wind in the other spot next to me, or what could be there in terms of topography, maybe, a big mountain, big lower fields, valleys. So you get to a point that to predicting the weather, you have to interact with all your different domain partners, right? The decomposed domain. And with this comes again, of course, now the idea was MPI to exchange data among this would be a very important part. And we learned already how to do it, right? With send receive, more smart when we have a big application would be using collective operations, like for instance, broadcast, scatter, or gather, and so. Hence, this is tremendously often used. And this is just one example, which is, I think, very apparent with a numerical weather prediction. There are news, however, that you can do similar things in AI. So this would be a complete different story. So AI just takes, let's say, data from historical, time series in account and predicts. So this is another newer trend that also this numerical weather prediction based on physical laws is augmented with, let's say, the history or learning from data, as we would call it in deep learning. But this is something which comes later in the course. As I said, we start with this in lecture 6. What is the impact of deep learning? Also in physics here and there. So it's an interesting insight of combining those fields indeed. Here we're talking just, solving a lot of partial differential equations of physics, fluids, and so on. And then basically have a relatively good understanding how the weather or any other physical process can be. But in order to do this, now that's important for you to get out of this lecture today, I decompose the Earth into smaller parts. And there are different models for it. Icon, for instance, has a more hexadecimal-oriented, domain decomposition, and so on. Hence, we look at this a little bit more from 10,000 feet. So there are different ways how you can do it. The domain decomposition you see here, we had already in 1D, in 1D with an array or vector is very straightforward, as we had also in the color coding. But what about the Earth now? The Earth is more tough, more complex. So when we want to, decompose it, we would also say now one processor each for everything might be not good enough. So I will maybe have the Earth bigger parts, chunked into bigger pieces and have more processors assigned, right? So in this sense, you see here one example of a processor decomposition, how you would compute this part of the Earth. Let's say whatever inside this could be Euclid-Salon, could be different parts of Goodfoss or so that you want to see and want to reproduce. You do a processor decomposition, and with this you assign, so to speak, the number of processors working for specific regions in this parallel program. And your parallel program needs now to understand and to think in that way, to work with it. Hence, this is your work as a parallel programmer to think about how you do this, right? I often gave also the pizza slice examples. When you have a pizza, and let's say you want to all count the salami on it here in the course. So what would be the smartest way to do? We cut it into smaller pieces, and each one of you is counting the salami, on it, or the pepperoni, as it is called here in Iceland. And then everybody gives the local, part of how many pepperoni are really on this pizza. Is it a good pizza? And then someone reports the global. The someone is, of course, now also something which often not is completely in the decomposition visible. So one other, this is a guy that maybe do the global calculation, might be a specific role, which is sometimes not really visible, but then of course leads to something called load imbalance later and elements, which we also still will discuss. So it looks beautiful, but of course to program that, this has been lots of interesting aspects we will discuss in this lecture, but also in the next one, lecture 4, and so on. Hence, you have many different ways how you can do it. You see here even blockwise chunks, cyclic ones, And this brings us also to the idea that we have a very data-oriented view on this. There are also functional parallelism when you have a data over a timeline, where you basically see that the different processors have certain different roles. So when you see this as an example here, it could be that you not think about now that you have just this domain. You could also think that you assign the processors in a way to have an atmospheric model. Then you have the land surface model and then the hydrology model. So basically all models to understand the water flow in a specific region, let's say in Jökulsárlón or so, close to the beach, where you also have then the ocean model fitting in, and they have to exchange information as well, but they're inherently parallel, solving their own problems, their own whole physics, their own data, and interchanging then in some respect only with the functions of specific forms. So this is another type we call function parallelism, and basically both are used in practice, and you can even have a name, so to speak, assigned to these elements, where you would say the data parallelism is quite known as single program multiple data, right? So you would say here in the earth science example with NWP, numerical weather prediction, you basically would say you have a similar earth structure, you have the idea of the topography, you have all the data in, and the same code, the same physics will apply, right? So this would be one approach to it. And this is often done. We have done this also already in our course in a way with having really the same MPI application. If you remember, just the rank told us where to go with some difference. Now, function parallelism would be then different. You would have maybe an expert code with multiple programs, multiple data involved, which will have very specific studies on it. Like, for instance, the head of the Formula One driver, which is very specific and not at all to be generalized to the car, as there are different head sizes, as you remember, and different sizes of the overall cockpit. And this might be a little bit something which is completely different than the code that is usually used for really understand what could be the best tires over certain tracks in a specific weather. So this is something where you have often also a master worker scheme, functional decomposition of codes, where we say it's basically multiple programs that interact with each other. Still, they all both want to solve a problem in a cooperative way. They have just another way how to do it. And we have more examples of this parallelization methods down the line when we come more to the applications, also when Reza will introduce CFD and so on later in the course. So what is also often done is basically parallelization of loops. This is made also something where you can have a sort of medium-grained loop parallelization here, where we have actually shared memory parallel programming coming up, where we also will learn that this is inherently supported by environments and libraries like OpenMP. So here you can say that instead of one processor doing the whole loop, you can actually crunch it down basically in two, as we say, decompose the domain of the whole 1,000 calculations here we do to something where both of the processors will do 500. And you see the way why this is possible, and then of course having a time which is shorter than doing the processor alone. The prerequisite is here, of course, that C and B are basically here independent from any other iteration in the array, right? Otherwise, it would be not so straightforward. Here we say it only depends on the current iteration. C is anyway a constant, but here's a very, very nice and trivial example how shared memory here could really do an interesting parallel domain decomposition again and computing on it, right? So we have it again on different levels. This is a very low level to medium grained level loop parallelization, while the functional programming we just had with a raced car and with numerical weather predictions, of course, a much, much bolder domain decomposition. And coming back to this, you can imagine if you zoom into this and if you make it more realistic, coming back to our shore in Iceland here, maybe somewhere in the Westfjords, we will see that you can do this in different ways. Again, the domain decomposition, even if you think you do a sort of grid display, you maybe also want to do something called Lattice, where you basically have different ideas how to do this mesh, if you want, in a way, right? This representation of the computational domain. What are really the data variables? Is it the information yet you have within the box or at the boundaries of these boxes, where the boundaries interacts? So this is one part of it. Another part of it is, of course, when you think about the computation complexity, it might be not always useful to have this pure sort of Cartesian grid around it that you see here, right? So there might meant to be different ones in domain decomposition that maybe simulate the reality much better. Also, when you think about load balancing, it's something we will establish. So some are maybe some areas are just much more computation expensive, maybe the interactions at the beach, rather than somewhere silently on the ocean with no clouds or so. So hence, we have elements where it's very computation expensive, and then the domain decomposition needs to be adjusted like this. And here's one of the examples, again, where I said we have not only this blocky grid, we can come out much to a much more smoother terrain here with the 3D lattice, where you see again, the nodes are really on the values that will be stored and computed on are not within this blocky chunks, but rather on the lattice corners, edges, and so on. So these are the things that you would then apply to the race car, to the actually logo of the course, which is now here prominently put, the airplane, but also as our previous examples where here at the beach, somewhere in Iceland maybe, where you then have to consider which one of those you want to do, and then putting it in a bigger scope of always thinking about, there would be an application logic, right? There would be some elements which have a certain role to play, one after another. You do an iterative way of simulating this. You don't simulate and compute all at once. So already this has something to do, which we will also see is a very important impact in the domain decomposition. Of course, then also towards the reality of this, making more realistic simulations really as we want to have. There are different options again, but it also depends, of course, of how much computing you have available. You can imagine this could be an interesting element again, maybe simulating some of the weather here in Iceland, where you have a very coarse-grained prediction, right? So this is really a huge kilometer scale covered. And of course, if you go down more into 110 as an example here in kilometers, you see it becomes all more realistic, looks all much better. But of course, you go there and have the price for it. So you need to have more cores available to basically really better this computing model. And then you can, basically never end, depending on your story and what you want to do with this. As an application scientist, do you want to understand precipitation, rainfall, ocean waves, wind, oil, storms? There are lots of elements, oil platforms can be put into the region, understanding what would happen in civil security's case, so to speak, if one fails, and then what happens to the ocean around it. Boats, fish, you can add more and more complexity to all of this, but it really depends what you want to do as an engineer or as an application scientist to really add more detail here. And so the beautiful news is with this, when you do this as an application scientist, MPI, what you already learned, gives us now the possibility to abstract from it, that we don't write the technical code really in a very low level send, right? So send, receive, I don't have to deal with any, sorts of IP addresses or anything which is underneath. The only thing I know is there are lots of cores, I can use them to my behalf. And that's of course a really pro. When you do this as a computational expert, you will understand that there's always application logic, which is also complex, right? Think about all the laws in physics. You're letting now a compute-intensive race car going through your processor, so to speak. Lots of, send, receives, lots of different messages to interact with the air around it, with the different parts, the stress on the different parts and different velocities of the car. And this needs to be all done over the time, or the heat in the room. We see here over time that will be an important factor of these simulations. This is really something where, now the idea of this domain decomposition comes in, and then also the idea of MPI comes in, because when you want to do this and want, for instance, the heat in the room computed, again and again, you also need to know what's happened, the time step now, basically in the other part, in the other domain decomposed part, right? It's not independent as we have seen in the methods. And there's here one example of a domain decomposition that I want to give you, because this has later on also something we call Stenthal methods, an important part that when you want to compute essentially the physics in this particular part of the domain, you rely on the neighbors. And this is a loaded statement. here, for instance, with the heat and so on, because that means you don't have that information, right? This is in the remain of other memory of other processors. Hence, you have to first send, or in this example, receive it also is this particular part of the domain to compute it wisely. Hence, you have always, let's say, a sort of time step inherently that in the time step where I compute, I need to be smart enough to have in the time step before already the end result given to me by the other processors. And this is something which is, so to speak, a little bit formalized across many of the different applications. Here's just a Jacobi solver for an example. But you can always imagine this like it is here in many of the applications, that the time step 0 is basically what informs already the time step 1. Right, in order to compute it wisely. And with shared memory, this is a little bit this gray part, it would be easy, but think about, you have also here and there processes that you can't reach with memory, then send and receive comes in. But how you can do this? You know, you have to think about, now we're quite limited. We have our data, we have our domain, we have it broken apart. So basically have a domain decomposition, but there's no space for data from the time step before, because I need this data from the time step I have now, especially if you do all the same. Hence, what the people introduced were these ghost layers, where really basically the name ghost already suggests there's a hidden trick that basically have some way of filling this data from the time step before, giving it at the end of the time step before to the other processor and vice versa, because they will have the same program. They also depend on the other processor. And here's a good example of these two fellows, where you would compute this in your time step 0, and then at the end of time step 0, the physics are known, you will, here in this example, send, receive the ghost layer. And of course, in a larger scale, this would be differently done. But here you can see this, that the ghost layers will be filled by the information from the time step 0, and then you're ready to compute time step 1 in the next iteration. Hence, there are always big loops, and it depends heavily on memory. It depends on the halo and ghost sizes of the cells. But this is how it's done to basically compute this interesting aspect of the time inherent elements of it. And there could be, of course, different ways how you do it. Again, to have this, kind of domain decomposition where it also reflects communication overheads. I would say the first is pretty trivial. Again, you would say, well, we have this, big chunk of a grid and we want to decompose it. So let's just do, 4 equal chunks here. But remember, in a parallel operation or parallel processing, we always have to interact with all of these different ones. Hence, there's some certain communication that you need here, which basically have an influence on the neighboring that we have just in let's say, low level had. Now on the big level, you see there's some communication overheads apparently to exchange the ghost layer input or the halo layers, right? So here you would say you have 3 times 16 that have to communicate, making it 48 in terms of communication requirements. So maybe there's another domain decomposition which is much more smarter. And that's the one you see here, right? So this comes more to this blocky element. And one reasoning is that you have just 4 times 8 elements to exchange in this domain. Hence, this is something not directly obvious to an application scientist, especially if you think you have an application logic that looks like this, maybe like a numerical weather prediction, lots of parts, which has to be considered to be accurate. But something also to understand. Equally, the example I already gave, so I will be a bit faster here. I told you the data science clustering example, I guess twice already, which we then solve with MPI. But you always have to remember from the domain decomposition, it doesn't look like nice that you see here. In the overlay, you already can imagine when you cluster these areas, it would be much more computing intensive areas and parts than perhaps here in this area. And more extreme, when you look at this, you see here, processor 1 and processor 2 are actually not divided in the middle, because processor 1 needs to do much more computing and perform the clustering, all what you see here in the end in this HPDB scan. So just to understand again, the domains are not always equal, right? The dots or you see here representing data science applications at large might be very unbalanced and distributed in a very, let's say, non-homogeneous way around your domain. So basically cutting the domain always equal will also be not the best solution always. So the equally important part is, before we come to the second part of the lecture, also think about the idea that there's always someone missing in these domains. Again, I would bring here the master worker scheme, really, where you think that you have the master that is doing this max global maybe of the array we discussed, taking the local elements of the maximum of the locals first, which we call then the workers, and then the master could be rank 0, for instance, would have then all the information and report. But then, of course, we can understand that this master has more to do than all the workers, because he is also sort of a manager, while at the same time taking maybe also his own elements of the domain. Or he's just responsible for shifting the data away that you see here and doesn't do anything but just doing the distribution, the collection, and reporting the maximum. Then you can better go against this load imbalance a little bit, right? So hence, this is something when you have a real physics application, and we will learn this again and again when you have more ground on the course later, when we have computational fluid dynamics with Razor, airflow, and so on, where you also then couple different areas where the physics are different and also the computational needs are different. But it needs to be also, taken into account with a communication perspective. And here you have a nice demo I found from the BSc. I will not play it here for YouTube, but of course be advised that here in the lectures that you then see in part 2, number 14, would be a good video to watch and understand a little bit more the applications now that we want to do with parallelization that actually in fact need HPC to work. So see you next time.